Okay, so this is the final topic with rotational kinematics. And then the next lecture, we will move on to rotational dynamics and look at the forces involved as well, because what provides the acceleration? We know linear force provides linear acceleration. So we will have a rotational force. We have an angular force that provides angular acceleration. All right, so that's for next time. But let's wrap this up with connecting our sort of English suvat with the Greek suvat, right? The linear suvat variable with the angular suvat variable. What is the connection? Obviously, there is a connection because if something rotates at a given angular velocity, it's a fair question to ask, well, what is the linear velocity at every point, right? So if it says however many radians per second, then how many meters per second is the tangential velocity? What's that? What's the radial velocity, right? Remember there's radial component and a tangential component. The radial velocity is 0 because here the linear velocity, the instantaneous velocity is going that way, right? So the motion is going that way. So it's tangent to it. So there's no VR that way, right? There will be centripetal acceleration, so radial acceleration, but not necessarily. Is there a tangential acceleration? Well, yeah, if this speeds up, if this is not constant, well, we did uniform circular motion where this is constant, but now we have angular acceleration, right? So this is not constant. Sorry, this is constant. This is constant, but that means this is not constant, right? This guy will increase. So if this guy increases, then the tangential velocity will increase, right? And so this guy will increase. So there is a tangential acceleration, and there is a centripetal or radial acceleration. You can use either one. Okay, in what we are going to be interested in. So we're sort of having the upgraded version of circular motion now. All right, so really this is the topic where a lot of students will get one of the more confusing parts of the course, not because it's anything difficult, but it's just there's a lot of formulas, and the formulas are very easy to get confused. Okay, so here's my advice to learning this part of the video is very simple. Don't memorize any of these formulas. You'll be glad to hear this, right? This is one of the time I say, don't memorize any of these formulas, okay? And understand how you get to the formulas and reproduce it when you need to, because it's very easy to get to the formula, and it's easier to get to the formula than to use the formula correctly and recognize the formula and use it correctly, all right? So I'll show you what we mean. All right, so first thing is let's connect theta to S, right? So if I went from here, if I rotate a certain angle over here, I have traversed that much distance. In fact, I really want distance. So we'll worry about the non-vector versions of this first. We'll worry about the non-vector version, and we'll worry about the vector version at the end later. All right, so notice there's no vectors above these, and I'll let you know what I mean if we promote these two vectors. But yeah, so what's the distance? Well, so let's call the distance here L, like this. Okay, so the distance went from, if the angle went from here to here, the distance of this particle, let's have a mass over here, went from here to here like this. Okay, so how much distance has it traveled? The distance traveled is L, right? So L. How does L connect to this? Well, if you remember, if you use radians, then it's very simple. Radians is L over R. Okay, if this is R like this, right? So let's use little r. Okay, why is it? Because radians, the definition is radians is defined as the arc length for a circle with radius 1, right? That is how radians is defined. Remember, if you forgot, watch the radians video again, and we have commented on that. But it's divided by r, right? So L is r the theta. The reason we didn't put theta before, or delta before, just have that. And the reason is because at the same angle, if the radius is twice as long, then the distance, so the arc length over here, that's subtended by the angle. Subtended means sort of projecting, sort of the opposite of projection. This is projection, this is subtension. So the arc length over here subtended by this, right? If I double the radius, I'll double the arc length. So the same angle, it's sort of proportional. The arc, if I sort of double the r, I'll get 2L like that, okay? But essentially, in radians, this is defined as if r is 1, then L is equals to theta, right? So that's a very simple connection. Since we're using delta now, so we'll use this, right? So the relationship is L equals this times r. That's it. Okay. How about velocity, angular velocity? Okay, so how do I get linear velocity? Well, linear velocity, the definition is the distance per time, right? So the rate of change of L per unit time. And so what we have is d dt of delta theta and r. You know what? Since I should put delta here if I'm being consistent. So let me call this length over as a function of time. So we'll shift to the formal approach since it's easier if I use derivatives. And yeah, so apologies for people copying notes. Right, all right, so that's the relationship there. Does the radius change in time? No, if it's rotating in a circle, then its radius doesn't change, right? So so what's the angular, how do they relate that? That's theta, that's r, but r doesn't change, so that goes out of the derivative. We only have d theta as a function of time times r, right? So this is angular velocity. So we have the first relationship is this, the second relationship is this. Okay. I'm making the t explicit so you know what is a variable, what is a function of time and what's not a function of time. Okay, so if you like, you can remember this version, but like I say, this is where it gets confusing. It's very easy to forget, hey, is it v equals omega r, or is it v equals omega divided by r, or is it omega equals vr, or is it omega equals v over r? So this is the part where I mean for students, right? It's very easy to mix up the equations, not because it's anything hard, but it's just easy to mix up. So however, figuring it out is, this is the one probably you want to memorize, all right? In some sense, that's the definition of radians. It's really definition of radians. Radians is, angle in radians is the arc length over the radius, okay? Arc length. And this is something I want you to learn as well, because it will be useful for the other physics courses. So if you understand, the angles in radians is arc length over radius, right? Then, so this or this is something you want to remember, others you can figure out, right? What velocity is this? Well, this is the velocity in this direction, right? So this is really the tangential velocity. So you can put that in as well. All right, so what is the angular acceleration? Finally here, right? And how does that connect to the linear acceleration? So linear acceleration, again, which acceleration am I talking about? I'm talking about how fast this moves, right? So it's really, right. So what I'm going to do is write dvt, the tangent. So I'm looking at the tangent acceleration. So how fast is it accelerating? I'm literally saying accelerating around the loop, not radially. Okay, so that we know, by the way, that you learned already. The centripetal one or the radial one, right, is the centripetal acceleration, right? Sorry, A, right? So you have part of A is in this direction, that's the tangent part, and there's a radial part which is causing it to change its direction. There's a part that's making it the tangent going faster and faster. This one is v squared over r, We've talked about that already. That's separate. Okay. That one, you want to remember it, but don't confuse. This is the radial one. Okay, we'll put it in box. All right, but this is, we'll put that on the side. Okay. Back to the tangent one, right? How would you do this? Is d dt. What's vt? Well, that's omega r. The r doesn't change. The omega is a function of time. So you have d omega dt, right? So this is alpha. Okay, so at is alpha r, right? So if you like, you can summarize L. So L equals to theta r. In some sense, it's the Latin variable equals to the Greek times r. The Latin variables equals to the Greek variable times r, and the Latin variable equals to Greek variable times r. But be careful. This is tangential component. Okay. You can a lot of people confuse that. If you, for example, if this is a constant, right? If alpha is constant, then it's change in omega over time, right? And that means it's also yeah. So that's the final minus initial over certain time. And can I replace, can I sort of massaging the omega over here? Maybe if I try hard enough. So if I start with this being 0, so I have omega t, right? So if I start something at rest, then I have this. So you see, it's very hard to get confused if you start from scratch and try and derive these equations. But let's see if I can get rid of the t as well. Probably not. Let's see what's the one that students do often. Oh yeah, they confuse that one with this one. There we go. Yes. So yeah. So here, since we know this, you can actually plug in here. So what's the velocity here? Which velocity is it? Well, there's only one velocity because there's no velocity going towards the center. There's only a tangent velocity. Even if it's accelerating, it's only a tangent velocity. So this is always tangent. So you could plug this in here and get omega square r. R is always a constant that never changes. So you get omega square r. Okay. And this is where, yeah, ignore that. We won't talk about that. So this and this is very similar, as you can see. That's why I was trying to massage in the omega. And as you can see, if you know where things come from, it's very hard to get confused. You will only get one answer. But if you try to memorize this, the big mistake I always see is students were given a tangential acceleration and they plug it in this formula. So understand one more time, at every point, before we deal with uniform circular motion, for uniform circular motion, there's only a centripetal acceleration. So it's only going here. There's no acceleration in this direction because if there is, it will speed up. But now we do care about potentially, right? There's angular acceleration, which means it will go faster and faster, which means the tangential speed, vt, will go faster and faster. So we do have this as well. And the formula for that is alpha r, and the formula for that is vt squared over r. Occasionally, if you're given the omega, you might need to use this. However, I would not even memorize that at all, as you can tell, because otherwise it's very easy to get confused, and derive it if you need, right? So I'll give you an example. If you are only given omega, right? If you're given omega and r, and it's asking you to find the inwards acceleration, the acceleration that is responsible for it to go in a circle, what you want to do is, so if this is your aim, don't use that formula. Just understand from before, well, it's vt squared over r, so now you need vt, it's the tangential speed. so VT is this. So find this first and use this to find this, right? So that will get rid of a lot of confusion and potential mix-up, okay? Now, we notice we have everything is in scalars. I haven't talked about the vector form. We'll wrap that up with talking about the vector form with and how to do that. And these equations will look like an upgraded version, which will look like this. In particular, the acceleration is going to be this cross R, okay? And the V is going to be omega cross R, like this, okay? So what does that mean? Well, we know what we know what R is. R is the position vector. So we start off so this is the position vector with the origin over here, or the displacement from the origin to a certain point. So this is the vector R. This is the vector V, right? And we'll talk about the acceleration as well. It's also the tangential one. But we haven't talked about what these vectors are, okay? And we also haven't talked about what does this mean. So we've talked about cross products. I have hinted about cross products, and this is where we need the cross products in order to define this. So we'll talk about that in the next video as well.